Hello dear students, welcome to mathematics class. In this class, let us discuss one important theorem on Riemann integral. So here it is the statement of the theorem. If f belongs to R of closed interval AB, means f is Riemann integrable on the interval AB, and k belongs to R, means k is any real number, then k into f belongs to R of closed interval AB, means if f is Riemann integrable and k is any real number, then we need to show that k into f, that constant into the function, is also Riemann integrable. And also we need to prove that integration over a to b k into f of x dx equal to k into integration over a to b f of x dx. Now, since k is a real number, then there will be three possibilities for the value of k. The first one is k may be equal to 0, or k is positive, or k is negative. So therefore, we need to prove the theorem in three cases. So let us prove case 1, if k is equal to 0. So if k is equal to 0, then what happens? Here k into f is there, so therefore 0 into f, that is equal to 0. So therefore, for any constant function, that function is always Riemann integrable. So therefore, if k is equal to 0, then the theorem is true. So for the 0, the theorem is true since constant function is Riemann integrable. So after multiplying 0 to f, this total becomes 0, which is the constant. So hence it is Riemann integrable function. Then case 2, if k is greater than 0, means if k is any positive real number. Now let f belongs to R of closed interval AB, that is f is Riemann integrable. So we know that if f is Riemann integrable, then upper and lower Riemann integrals are must be same. So therefore we can write bar a to b f of x dx is equal to a to b bar f of x dx. That is the lower Riemann integral is equal to upper Riemann integral, which is equal to the common value of the integral, that is Riemann integral, that is integration over a to b f of x dx. Let us consider this as the first equation. Now, since f is bounded, so here f is Riemann integrable, means that should be a bounded function. So therefore, since f is bounded, then it implies that k into f is also bounded. Since f is a bounded function, then if you multiply any constant term to the bounded function, then the product of them is also a bounded function. Let p is equal to a equal to x0, x1, x2, so on up to xn equal to b, be the partition of the closed interval AB. So now let us consider the partition whose points are x0, x1, x2 up to xn, and IR is equal to the rth sub interval is given by xr minus 1 to xr. So it is the rth sub interval of the partition P, and these are the points of the partition P. Now let small mr and capital Mr be the infimum and supremum of the function f on rth sub interval IR. So here let us consider small mr and capital Mr. Small mr is the infimum and capital Mr is the supremum of the function f on the rth subinterval IR. So therefore, we can write k into mr and k into capital Mr. So here, since these are this mr and capital Mr, these two are the infimum and supremum of the function f, then if you multiply the function by k, then these two, infimum and supremum, becomes k into mr and k into capital Mr. So therefore, k mr and k capital Mr be the infimum and supremum of k into f on the rth subinterval. So here we have considered the infimum and supremum of both the functions f and kf. So for the infimum and supremum of the function f, if you multiply the constant k, then those two will be the infimum and supremum of the function kf on the rth subinterval. And then now here we need to prove that kf is Riemann integrable. So that k into f is Riemann integrable. So we need to show that upper Riemann integral and lower Riemann integral of that kf are one and the same. So therefore, now let us consider the lower Riemann integral, that is bar a to b k into f of x dx. So here, this is the lower Riemann integral for the function kf, that is k into f of x. So by the definition of lower Riemann integral, we can write this one as supremum of all lower sums, that is LPKF. So here, lower Riemann integral means that is the supremum of all lower sums of the function f. But here the function is k into f, so that's why we are considering LPKF, means it is the lower sum of the function kf on the partition P. Now it is equal to supremum of, now by using the summation form of the lower sum, that is summation over r is equal to 1 to n. While finding the lower sum, here we are using the infimum of the function. So since the function is kf, then its infimum is given by k into small mr into delta r. Now this can be written as, since k is constant, we can take it out of the summation. So therefore, that is k into supremum of summation over r is equal to 1 to n small mr into delta r. So since k is constant, we can take it out of the summation. Since it is constant, then it doesn't make any difference for the supremum value of that summation. So hence we are writing that as k into supremum of summation over r is equal to 1 to n small mr into delta r. Now this one is equal to k into supremum of. Now by using the formula summation over r is equal to 1 to n mr into delta r, this summation is nothing but lower sum of the function f, because this mr is the infimum for the function f and k into mr is the infimum of the function kf. So therefore, this is the lower Riemann sum of the function f on the partition P. So therefore, it is k into the supremum of lower sums, that is nothing but lower Riemann integral, that is integration of bar a to b f of x dx. And now this can be written as k into integration over a to b f of x dx. This is by using the equation 1, because in equation 1 we have that the function is Riemann integrable. So therefore, upper Riemann integral of the function f is same as the lower Riemann integral of the function f, and those two are equal to Riemann integral, that is common value integration over a to b f of x dx. So this is by using the equation 1. So therefore here lower Riemann integral of the function kf is equal to k into integration over a to b f of x dx. Now consider this as equation number 2. And now let us consider the upper Riemann integral, that is integration over a to b bar k into f of x dx. Now again, by using the definition of this upper Riemann integral, it is nothing but infimum of upkf, and now it is equal to infimum of, this is summation over r is equal to 1 to n k into capital Mr delta r, because it is the upper Riemann sum of the function kf, and while finding the upper Riemann sum we need to use the supremum of that function, that is nothing but k into Mr. So therefore the same expression can be written as k into infimum of summation over r is equal to 1 to n capital Mr into delta r. So here k is the constant, so therefore we can take it out of the summation, hence it is k into infimum of summation over r is equal to 1 to n Mr into delta r, and this is equal to infimum of, and this is the UPF, upper Riemann sum of the function f on the partition P. So therefore it is equal to k into infimum of upper sums is nothing but upper Riemann integral, that is a to b bar f of x dx, hence it is equal to k into integration over a to b f of x dx. This is also by using equation 1. So here integration over a to b bar, that is nothing but integration over a to b f of x dx. So therefore integration over a to b bar k into f of x dx is equal to k into integration over a to b f of x dx, and consider this as equation number 3. So now by using the equations 2 and 3. So in equation 1 we have integration over bar a to b k into f of x dx is equal to k into integration over a to b f of x dx. It is the second equation. And in third equation, a to b bar k into f of x dx equal to k into integration over a to b f of x dx. It is our second equation, and this is the third equation that we already know. Now by comparing these two equations 2 and 3, here we can see that in both the equations RHS part is one and the same. Here also it is k into this integral, and here also k into the integral. If RHS of any two equations are same, then their corresponding LHS must be equal to same value. So therefore it implies that integration over bar a to b k into f of x dx is equal to a to b bar k into f of x dx. Now here we can see that this is the lower Riemann integral of the function kf, and this is the upper Riemann integral of the function kf. So now we are getting these two as equal. So if the lower and upper Riemann integrals of any function are same, then we can say that that function is Riemann integrable function. So therefore k into f of x is R integrable. K into f of x is R integrable, or we can write symbolically as k into f belongs to R of closed interval ab. So therefore we can write that integration over bar a to b k into f of x dx is equal to integration over a to b bar k into f of x dx. Since these two are same, then their common value can be written as integration over a to b k into f of x dx. So therefore now by using equation 2 or 3, we can replace this bar a to b k into f of x dx by integration over a to b k into f of x dx. Is it right? Here you can consider this as equation number 4, right? Now you can use 2 and 4 or 3 and 4 to write the result that. So now here from equations 2 and 4, integration over a to b k into f of x dx is equal to k into integration over a to b f of x dx. So here in equation 2, that LHS bar a to b k into f of x dx, that can be replaced by integration over a to b k into f of x dx, that we have replaced here, and this RHS will be same, that is k into integration over a to b f of x dx. So this is the required result. Now it is the proof of the theorem for second case, means for the positive values of the k. And next we need to show the result for negative values of k. So therefore let us consider case 3. So if k is less than 0, means if k is negative, then let us see what will happen. Now here it is given that let f belongs to R of closed interval AB, means f is Riemann integrable. So therefore we can write that bar a to b f of x dx is equal to integration over a to b bar f of x dx is equal to integration over a to b f of x dx. So this is because f is Riemann integrable function in this interval AB. So let small mr and capital Mr be the infimum and supremum of the function f on Rth sub interval that we have considered previously. Now here, since k is negative, then if you multiply any number by a negative sign, means its value will decrease. For example, here we have 2 is less than 3. Then if you multiply this inequality by negative sign, then what becomes? Minus 2 is greater than minus 3, right? So here this is the infimum and this is the supremum, and the value of k is negative. In the previous case it was positive, then there will be no difference in the supremum and infimum values of f and kf. But here if you multiply this small mr by this value of k, then it is the infimum for the function f, then k into mr becomes the supremum of the function kf, since k is negative. So therefore k into mr and k into capital Mr be the supremum and infimum of k into f on IR. So here supremum and infimum of the function f are get reversed because k is negative. So therefore here k into small mr is the supremum of kf and k into capital Mr is the infimum of kf, whereas small mr and capital Mr, these two are the infimum and supremum of the function f on the Rth sub interval. Now consider lower Riemann integral, that is integration over bar a to b f of x dx, sorry, k into f of x dx. Now it is equal to supremum of all the lower sums of the function kf, that is LP kf. Now it is equal to supremum of, this one is summation over r is equal to 1 to n. While finding the lower sum, we need to find the infimum of the function kf. So here infimum is k into capital Mr into delta r, and since k is constant, we can take it out of the supremum and summation. So therefore this becomes k into supremum of summation over r is equal to 1 to n capital Mr into delta r. Now this one is equal to k into supremum of, so here this summation over r is equal to 1 to n capital Mr into delta r. This capital Mr is the supremum of the function f. So therefore this summation is nothing but upper Riemann sum of the function f. Now here we don't know the value of that supremum of UPF, because supremum of UPF is simply it is the supremum of upper sums, but if we are considering supremum of the lower sums, then that will be the lower Riemann integral. So now here the value of k is negative. So therefore whenever we are multiplying by the negative sign, then supremum becomes the infimum and infimum becomes the supremum. So therefore this becomes k into infimum of UPF. K into infimum of UPF, because of the condition that k is the negative value. So therefore this becomes k into integration over a to b bar f of x dx, right? Because infimum of upper sums, that is nothing but upper Riemann integral. So therefore k into integration over a to b bar f of x dx, and this can be written as k into integration over a to b bar, integration over a to b f of x dx. This is bar a to b k into f of x dx. So here lower Riemann integral of the function kf is equal to k into integration over a to b f of x dx, and consider this as equation number 5, because in the previous case only we have 4 equations and this is the 5th equation. So here this a to b bar, here we have a to b bar is nothing but integration over a to b, so therefore it is integration over a to b f of x dx, and this is the result for lower Riemann integral of the function kf. And similarly we need to find the upper Riemann integral of the function kf. Integration over a to b bar k into f of x dx is equal to infimum of all the upper sums, infimum of UPKF, since it is the upper Riemann integral. Now it is equal to infimum of, so by using the formula in the form of summation over r is equal to 1 to n, and infimum of kf, for upper sum we need to find the supremum of the function kf. Here the supremum is k into small mr delta r, and again we can take that k outside, then k into infimum of summation over r is equal to 1 to n small mr into delta r. Now it is k into infimum of, again by using this summation form we can replace this summation by, that is the lower Riemann sum of the function f. Now we know that k is less than 0. If k is less than 0, then infimum becomes the supremum. So therefore it is k into supremum of LPF. So therefore supremum of LPF, that is nothing but the lower Riemann integral, that is bar a to b f of x dx. So therefore it is k into integration over a to b f of x dx, and it is the 6th equation, and here it is a to b bar f of k into f of x dx. So therefore integration over a to b bar k into f of x dx is equal to k into integration over a to b f of x dx, and again this lower Riemann integral is same as the common value of the Riemann integrable, since f is R integrable function. Now from equations 5 and 6. So in the 5th equation we have integration over bar a to b k into f of x dx is equal to k into integration over a to b f of x dx, and here it is a to b bar k into f of x dx is equal to k into integration over a to b f of x dx. So now by using these two equations, so by comparing these two equations, LHS of these two equations are different, but the RHS are one and the same. So therefore we can write the result as integration over bar a to b k into f of x dx is equal to integration over a to b bar k into f of x dx, because in this equation these two are distinct, but these two are same. If the RHS of any two equations are same, then the corresponding LHS will be same. So therefore, we got the result as lower Riemann integral of the function kf is equal to upper Riemann integral of the function kf. So therefore, it implies that k into f of x is R integrable. It is the R integrable on the interval AB, or we can write this as kf belongs to R of closed interval AB, since upper and lower Riemann integrals of that function are one and the same. Now here kf is Riemann integrable, so therefore this bar a to b k into f of x dx is equal to integration over a to b bar k into f of x dx is equal to the common value, that is integration over a to b k into f of x dx. So therefore, here we can consider this as seventh equation. Now from equations 5 and 7, from equations 5 and 7 we can write that integration over a to b k into f of x dx is equal to k into integration over a to b f of x dx, because in equation 5 we have that lower Riemann integral is equal to, here it is, bar a to b k into f of x dx is equal to k into integration of a to b f of x dx, and here we are replacing this by the common value of the Riemann integral, that is integration of a to b k into f of x dx. So therefore, integration of a to b k into f of x dx is equal to k into integration over a to b f of x dx, which is the required proof. So therefore, in this theorem we have proved that if f is the Riemann integrable function, then k into f is also Riemann integral in the same interval AB, and also integration over a to b k into f of x dx is equal to k into integration over a to b f of x dx. So in this theorem we have three cases. In the first case k equal to 0, there is nothing to prove, and remaining two cases are important, k less than 0 and k greater than 0.